All right, so looks like I'm live. So welcome back to M17 Labs in Warsaw, Poland. My name is Wojciech, and today we are going to code some more VHDL for the OpenHT. And today we are going to focus on the CTCSS encoder. So let's start with some basics. So maybe let's say what the CTCSS actually is. It's a tone coded squelch for analog FM systems. So normally, when you take your radio uh, and use it with analog FM, sorry, uh, normally you set the squelch level so that the you don't get too much noise in the speaker, because if there is no transmission, there is just noise, and you want to avoid that, and you don't want to listen to voice. You want to the speaker to actually emit speech and some kind of sound that is pleasant to listen to, not the noise. So normally you set the squelch level to some threshold, and you can't hear anything below it. If the signal is too weak, you are not going to pick it up. And if the signal is strong enough to reach the threshold, the signal from the modulator makes its way to the speaker. So that's how the the signal strength based squelch works. And the CTCSS works in a similar way, but instead of uh, checking what's the signal strength, you actually demodulate the signal first and then check if there is a not audible tone within that signal. So you take a look at the baseband and see if the tone is present. If the tone is present, you just unlock the squelch, and the tone's frequencies are below 250 hertz, I believe. We've got a table of all of the CTCSS codes. Even some of them are not really supported by the TIA standard. Because normally I believe you have 38 CTCSS codes or tones that basically any analog FM radio support. So you can grab the cheapest Baofeng that you can get, and it's going to support CTCSS. So it's like in every radio. So let's have it in OpenHT 2. So to do that, let's take a look at the internal structure for the OpenHT, and let's take a look at the frequency modulator. So it's this block right here. So we've got the frequency modulator that takes the frequency tuning word from a register, and the register is register 9. So we take that value, it's a 16-bit signed integer. We take that value, send it to the frequency modulator block, and it just outputs I and Q stream for the 8086 IQ transceiver. So this is what you have right now, and it works. So you can present the ADC of the STM32 with your baseband. So that can be speech, that can be music in theory, so any signal. And then you can also present it with M17 baseband, and it's going to work just like that. It's this one. Yeah, so we've got the register that holds the baseband value, and it's passed over to the frequency modulator. So the CTCSS tones are actually, they are not audible. They are also filtered out, just to be sure, at the receiver part. I believe the Baofengs and other radios just filter out anything below 300 hertz, just to be sure, because the highest tone is just over 250 hertz. Yeah, so compared with the speech signal in the analog FM, the CTCSS takes about, I believe, 10 to 15% of the signal. So it's not very strong. It doesn't have to be strong to be detected at the receiver. So what we have to do is we have to add a signal generator somewhere between the register and the frequency modulator. Sorry, it's this block, not this one. So we have to create a block that's going to generate the tone for the CTCSS. And before we generate the tone, we actually have to know which tone to use. And if there are 15 tones available, we also want to have one additional, let's say, tone that's going to have value of 0. So that's going to disable the CTCSS if we don't need it. So let's say 51. So the log with the base of 2 of 51 is about just less than 6, I believe. Let's do some maths. Of course, 64 is to the power of 6, if I remember correctly. Yeah, so that's going to be just less than 6. For 51 entries, we need 6 bits. Yeah. Oh, all right. So we need to take one of the registers to hold the CTCSS tone value from 0 to 51. No, from 0 to 50. And then translate that value to a frequency, actually to a frequency word for the oscillator. Then take the oscillator output. That can be either sine or cosine, it doesn't matter. We already have the lookup table that is able to output both sine and cosine, and we can just discard the other one because we can use either one of those. It doesn't matter. The phase doesn't matter in our case. And then we take that signal and we have to shift it right by, let's say, 4 bits to make the amplitude a little bit smaller, and then add it to the signal that we read from register 9. Yeah, this one. And after that, it should work, and we should be able to test it. And our test setup is an USRP B210. We've got the GNU radio blocks already configured to receive on 2.4 gigahertz, because that's the frequency that we are going to use today, 2.4 gigahertz sharp. That's, of course, the ppm correction for the USRP. It doesn't matter. Yeah, so that's our receiver. Let's see if it still works. Yeah, it does. So right now there is just a carrier at 2.4 gigahertz. Continuous wave, so no signal modulated. No signal is being modulated. So that's the spectrum, just noise with some random peaks that we don't care about. Okay, so right now we've got the frequency modulator running in the OpenHT, and the input to the ADC is just half of the supply voltage for the ADC or the STM32. And that, of course, corresponds to a carrier wave, just a continuous wave at the mid-range for the frequency range of the NCO. So we've got a nice let's actually take a look here. This view is probably better than the one that you see on the right-hand side. So this is okay. So this is the signal that comes out from the OpenHT over actual air. So we are transmitting over RF. The distance is very short, is about 10 centimeters. And the signal strength, the signal power is, I believe, 10 milliwatts. All right, so that's our signal. And now I'm going to apply a 1 kilohertz sine wave. So we need to do this. I'm looking at my signal generator. And in just a second, you should be able to see a nice modulated carrier. All right, so the frequency is set. That's our signal. Of course, that's expected. That's a 1 kilohertz modulated carrier with nothing else, just the sine wave of 1K. Let's take a look at the modulated signal from the USRP. Let's zoom in. And as expected, we've got a large peak at 1 kilohertz. Yeah, all right. So now we are going to do this. We are going to prepare the CTCSS block for the OpenHT. We are going to implement it into the FPGA and then reset the FPGA and see if we get a nice peak at, let's say, 127.3 hertz. I believe that's the tone number 20. Yeah, so that's one of the standard tones used in Poland for analog repeaters. So we are going to use this one. We can, of course, use any value from this list, but I think we can try actually something else. We can try and map first 5 values for the frequencies, then try one of them, because this tone is 20th in the list, so that's going to take a while to calculate all the corresponding tuning words for each frequency in the list. So we're going to try and do this. Let's first try and prepare the CTCSS block. And it's going to incorporate the lookup table, the NCO, and a simple map that would map the 6 bits from the register, from one of the registers to the frequency word. And the frequency word is going to be 21 bits. Let's take a look at the frequency modulator. So the input to that block is mod_I, and that's 16 bits. So we take that 16 bits, and then it's this. So it's treated like a standard logic vector, and later on it's casted on a signed integer. So we take this, and this is where it's casted to a signed integer. Then, of course, resized because the phase accumulator is 21 bits in this case. So the phase accumulator is going to be 21 bits in our case too, because we are just going to copy over a part of this code. So we don't have to reinvent the wheel. Then we are going to use this phase to get a value for the sign from a lookup table. Yeah, okay. So let's, so the tuning word is going to be 16 bits, I believe. signed, but in our case, we actually don't need the sign because CTCSS codes are just sine waves, and we don't care if that's a positive or negative frequency, so we don't care about the phase. All right, anyway, let's copy over this part of this code, and let's generate new block. It's new file. CTCSS encoder. That's going to be VHDL file, of course. All right, no typos. I believe that's okay. All right, so we are going to reuse a large part of this code. Of course, it's April. And all right, that's phase modulator. Yeah, CTCSS encoder block. That's nice. CTCSS encoder. We don't need the generic part for the divider, or do we? So the divider was used to the divider was used to is used to divide the incoming clock signal, that is 38 megahertz, to get 400k signal. So in this case, that's 95. But for the CTCSS encoder, we are not going to need that because we are going to feed it with the 400k signal. So we don't need the divider, I believe. Let's remove it for now. CTCSS encoder, that's our entity. All right, so do we need the reset pin? Let's leave it for now. The clock input, that's going to be 18 megahertz clock to check if there is a rising edge at the trigger input, because we need the trigger to know when to increase the phase accumulator. Modulation in, of course, that's needed, but not exactly like this, because the modulation in actually is a value from a register. So if we take a look at the register map, we've got 6 bits, more than 6 bits spare in this register, number 1. So we are going to go ahead and use bits from 7 down to 2 as the input. So we need 6 bits. Maybe not code. CTCSS input. Yeah, so if we don't want the CTCSS, we can just set it to 0 and add some logic later on to detect that and just disable the NCO, the oscillator. Dithering, I don't believe we need that. Let me think for a second. We actually might need that, but maybe not right now, not immediately. Then we've got I and Q data out. We just need one signal to be output from this block, so we're going to name it CTCSS tone output. All right, so that's much better. And that's, of course, going to be 16 bits. Okay. Even if we are going to use just 10 bits or so, we need this output word to be 16 bits because we are going to add that value to the value from the register number 9, and that's 16 bits. So we need this to be 16 too, to avoid resizing the vector later on in the main.vhd file. All right, so we don't need this component. We of course need the phase. This is not needed. The phase word is going to be 21 bits. This lookup table is needed. Of course, we need to change the name of this. All right, so that's it. Now the lookup table. Let's make this a little bit more readable by doing this. And this is much better. All right, so the phase is 10 most significant bits from the phase accumulator gets passed to the theta of the lookup table. And the lookup table is, of course, 1023 or 24 entries long. 1024, I believe. Yeah. So that's this one. We don't need the cosine. I believe we can just comment that out, and the VHDL parser is not going to cry about it. So the sign output from the lookup table can be actually fed straight to the CTCSS output, because the output is 16 bits signed. Let's make sure if that's the case. Syncos. The output is standard logic vector, but that's 16 bits. And according to what I see here, if the sign starts at 0, it goes up, then and ends at this value, it looks like those values are signed. So let's get back to this one, this file. All right, so we've got the lookup table getting the right phase and outputting the sign to the output of the block. Now the phase differ, we don't need that. And let's remove it. If we need that later, we can add it later. But right now it's not needed. All right, and the clock is used to detect rising edge of the trigger in. Oh, we of course need the trigger input. That's going to be input standard logic. The trigger input is used to tell the phase accumulator to advance, to add another, to increase or advance in value. This value should be 400K in our case, just because we have set, we have this this signal in the netlist analyzer, and that's probably this one. Yeah, the 0 word signal that is used to pass 0 words to the 8086 is actually 400 kilohertz. So we can use that signal for the phase accumulator, and we are going to do it. That's the FM. All right, so we don't need this anymore, at least now. CTCSS tone in and out. That's of 6 bits value. That's 16 bits. All right. And the trigger, the main clock, that's going to be probably 18 megahertz in our case, but it doesn't really matter as long as it's faster than this one, at least twice as fast. That's a safe spot. All right, so this is done. The Synco slot is done. So we probably don't need this. or do we? All right, let's focus on this first. We are going to need to detect the rising edge of the trigger input. But before we continue, let me check Discord or the chat. No comments in the chat. And no comments on Discord. All right, so let's proceed. Yeah, so we need to detect the rising edge at the trigger input. And to do that, we are going to add two D flip-flops and two signals, previous trig input and previous trig input. That's going to be standard logic, and of course we want to set that to 0 as the default value to make it a little bit more readable. Okay, so now at the rising edge of the clock, we have to push the trigger input value to those two signals. So let's start with the first one. That's going to take the value of the trig input, and the PP trig is going to take the value of P trig. So in our case, those are two D flip-flops that are just going to delay the trig input, so you can detect the rising edge just by using an AND gate with one of the inputs inversed. All right, so let's do this. Let's detect the rising edge of the P trig. So if the PP trig input was or is 1, no, is 0, and P trig I is 1, then yeah, it's been a while since I have coded in VHDL, not counting the phase modulator block. Yeah, so if the two flip-flops detect a rising edge at the trigger input, then we can actually advance the phase. So we can take this part of the code. Yeah, so the phase is going to be phase plus, that's not actually right, because we need to map the frequency words to CTCSS inputs. But for now, just to check if that actually works, we can do this. We can take one of the frequencies. Let's take the 127.3 hertz and check what's the tuning word for that. So 29B in hexadecimal. All right. All right, so let's do this. Do we need this counter? No, we don't need the counter. Oh, and of course, if the reset is not 0. Yeah, so if there's a rising edge of the trigger input and the reset is 1, the NRST, so that's inverted reset. So we don't need this anymore. Oh, actually, this can be used here, and instead the output can be set here. That's going to be a little bit better, but of course not here. This is a better place for that line. Yeah, we're going to rearrange something here because that doesn't look good. So if the not reset is held high, then do this, and else do this. Counter is not needed. The phase can be zeroed out. All right. So now what we need is the value to use for the phase accumulator. So how to do that? Actually, we've got the phase word that is 21 bits, and we want to add let's comment this out. We want to add this word to 9b. So that's the most naive approach that I can think of. We need probably one more parenthesis. Yeah, so we are going to add phase to 29b. That's 12 bits, and we want that to be 16 or 21. 21. So we have to resize that. We want to resize that to 21 bits. So what the resize function does is for an unsigned value, it just prepends the value with zeros to get the correct bit length of the vector. And if that's a signed value, then it just repeats the most significant bit, that is the signed bit, until we get, in this case, 21 bits. So we've got 12 here. We are going to prepend it with some zeros to get 21 bits. Now let's save this file. Of course, there is an error because probably we have too many parentheses. Oh, of course, this is not needed. Another typo. Oh, what now? That's line 50. Okay. Maybe we need to use this. Not quite. All right, so how do we proceed? Do we need to do this? Still the same problem. All right, let's think about it for a second. We need an unsigned value of this. Let's try and declare a signal, I don't know, whatever, as a standard logic vector. No, that's not going to work, because if we pass that value of 29b to this, we are going to end up with the same problem, probably. But can we do something like this? Of course, I'm experimenting with VHDL. I have no formal experience with it. This is not going to work because this value is 12 bits. Yeah. So we have to expand that to 21. And to do that, we're going to add some zeros. Can we try and actually use the concatenation operator here? Yeah, we can. So we are safe. So that's 12 bits. So we need 9 more. So that's 8 and that's 9. Okay, so looks like it worked. So we can use this value here. We don't need to resize it anymore, I believe. We just have to tell it that it's unsigned value. Yes, it worked. So now we add the test value. So that's the tuning word for 127.3 hertz CTCSS tone. And that value is going to be added over and over again to the phase accumulator, and the phase accumulator is going to the 10 most significant bits are going to be used for the theta, for the lookup table. So let's now go back to the main VHD and the netlist analyzer and actually connect this block to the phase modulator, the frequency modulator, and we can probably do it right here. So first of all, is this already in the list, this file? Yeah, it's here. Let's move it up. CTCSS encoder. Let's move it here. All right, so now we have to redefine this entity within the main VHD, and we can do it probably somewhere here. Control registers, SPI, modulation selector, sideband, IQ offset. We can try it. We can try and move it here. That's not entity anymore, but instead it's a component. Okay. Now we can actually copy over this part, make it pretty, align with those comments. Perfectionism. It's going to kill me someday. CTCSS encoder. All right. So let's go back. Where's the place? Frequency modulator. Right here. That's going to be CTCSS encoder 0, CTCSS encoder port map. Okay, so the NAT reset is going to be connected to the NRST global NAT. Trigger input is going to be connected to the 0 word. That's 400K. The clock input can be tied to the global clock input, which is 18 megahertz. The input for the CTCSS tone, I believe we will have to use just 6 bits zeros because we are not using that for now. And the output from the CTCSS let's call that CTCSS, maybe S like signal, or R like register. Yeah, okay. Doesn't matter. For now, we are probably going to change all the names for the variables and signals because they don't really make sense. But for now, it's okay. Let's go back to this place where all the signals are defined and add another signal. Maybe not here because that's not going to make any sense. Let's try and let's try this place. Signal. This is STT logic vector. That's of course 16 bits. All right. Yeah, looks good. All right, so that's the output. Now let's get back to the frequency mod. All right, so the reset is done, 0 word. So the 400 kilohertz signal is done. The clock input is there. This is not needed, so we are just passing random stuff. Actually, this is just 0. And then the CTCSS output, that's going to be the sine wave. But there's one small problem that we have omitted. The output from the lookup table is going to be 16 bits, but we don't need 16 bits because that's going to be a very large signal for the modulator. So instead, let's see, it's right here. So the CTCSS output is gets the value from the raw input, and the raw input is, of course, the let's call it row R. It's not an input, it's a register. So this gets the value from the lookup table. So that's 16 bits. So actually, let's do this. Let's take the most significant part of that. Let's omit if the signal is supposed to be 10% of the analog baseband, the modulating signal, I mean, that's 1/10. So maybe 4 bits should be enough. Yeah, 3 bits it's not enough. So let's go for 4. So 0, 1, 2, 3. So down to 4. So that's going to give us how many bits? Oh, I'm lost. It was 16 and we just discarded 4, so that's 12. Yeah, 15 minus 4 plus 1, that's 12. That's good. That's good. And of course, we need to resize that back to 16. So it just took the most significant part of the row register, holding the value for the sine wave. So this is an equivalent of dividing by 2 to the power of 4, so 16. Okay, so this node can be saved. No. Why? Standard logic vector, of course. For the CTCSS, the expected value is the expected type is standard logic vector. Of course it is. Unresolved signed. Very nice. Right, so let's try and force it to see signed value. Yeah. So in VHDL, something like this is completely normal. I know it's ridiculous, but yeah, okay. All right, so that's it. No errors. Now let's get back to this file. That's the top level file defining all the interconnections between the blocks. So we now need to connect the CTCSS encoder. Maybe instead of using just random zeros, a random value, a magic value, let's take a register 1 bits from 7 to 2. Now, what's the name of that? I believe it's this one. So we need the register 1 and bits from 7 down to 2. Is that correct? 7 down to 2. Yep. Hopefully, no errors. Probably because the global reset is just called reset. And yes, it is. Okay, so this is resolved. No errors. Let's try and synthesize it just to see if the connections are correct. So fingers crossed. This is not going to be a very long process, I believe, because we only synthesize the design, so we don't map it onto the FPGA yet. No comments on Discord. Am I even live? I hope so. Looks like I am. All right, so the synthesizer is done. I need to check the chat on YouTube, actually. Can't see anything in the chat. Yeah! Aligned code. Yeah, actually, this is not Python, so you can have everything in one line, and it's going to work just fine. And I really don't like Python, by the way. I'm not a big fan of VHDL either, but actually I can do something in VHDL, and it even sometimes works. So I like VHDL a little bit. All right, so let's take a look at the connection between the register map and the frequency modulator. So that's register 9, I believe. Yeah. So register 9 goes to the frequency mod. And what is happening here? Yeah, we've got register 1. That's, of course, just a part of it. That small triangle notifies me that we are just taking a small part of the bus further. So this is 16 bits, and this is not 16 bits. How much is it? We don't know. The register is 16 bits. All right. Actually, we know that it's 6, but it's not. You can't tell just by clicking on it. You can tell by clicking here, but yeah, you can assume that the lengths of those vectors are the same. All right, so we've got the CTCSS encoder block already connected to the clock, the global clock that is 18 megahertz. Then we've got the reset line connected. Then we've got the trigger input, which is 400K. And then the CTCSS, of course, it's connected to the register that holds nothing, all zeros. And now, to check the block, if it really works, we need to add an adder. So we have to combine two signals together, and the result, the sum of them, should be routed right here instead of that just row number 9 register value. Okay, so let me confess, I wanted this stream to be as short as possible, so I avoid talking for like almost 2 hours on some technical and VHDL stuff. And I just wanted to show you how it works, but in VHDL, it's not that easy, and it's not possible to do a short live stream on VHDL coding and FPGA stuff. All right, so the CTCSS block should be working right now, so all we need is an adder. So let's try and do this. Let's take this signal, which is 16 bits, and that's a signed value. Actually, the output is unsigned, but for the other, I believe it doesn't matter if the signal is signed or unsigned. So the other just adds the values together and doesn't care. And add it to this. So this is register 9. Okay, so we need one more signal. We need one more. Actually, not a signal. It's called a signal in VHDL, but in reality, it's a bunch of wires. So instead of a signal, we're using a bunch of wires. So let's try and let's add it here. Okay, let's name it CTCSS FM TX. I know those names are very, they are not really self-explanatory, but we need to rename them later. Of course, we need a standard logic vector. And this time, oh, not only this time, it's 16 bits. All of the bits set to 0 as an initial state. Now, how to do the addition. So that's one of the inputs. Then let's add it here. We need to do something like that. We need this to be let's try with this, and then we are going to add a bunch of functions that will tell VHDL what actually this is, because it's just a logic vector, so VHDL has to know if that's signed or unsigned or whatever. So the CTCSS FMTX is CTCSS R, which holds the CTCSS signal. Then we have to add the value from register 9. And now we can just swap those together because the modulator is going to take this. And the CTCSS is actually unsigned. And the value in the register is signed. I believe it's not a problem to add signed and unsigned values, but let's try and let's see. And the CTCSS FMTX, that's a standard logic vector. So we need to cast that back to the standard logic vector. Of course, it doesn't work, because why should it work? We've got an unsigned value plus signed value that we cast to a standard logic vector. And for some reason, that doesn't work. Now, why? I miss one thing in Lattice Radiant, that is something like giving me a tip on what the variable is, what the signal is. If I just move mouse pointer over it, it should tell me that it's a standard logic vector 15 down to 0 something, but it doesn't do that. And I have to scroll up, find where it is, and then see for myself. That sucks. Yes, this is this one. So both are standard logic vectors, 16 bits. So what is the reason why it doesn't work? The register value is, of course, standard logic vector. Let's make sure that's the case. Of course, that's not defined in this file. It's defined in this file. No, not control rex. Rex package. It's an array of standard logic vectors. Yeah, as expected. So back to the error. Of course, oh yes, we can click on it. So what's going on? We've got the two logic vectors casted to signed and unsigned, and you just can't add them together. And the size match because that's 16 bits, that's 16 bits too. Who likes Python when you have C? C is the best language on earth, and deal with it. All right. What's wrong? What if we try and do something else instead? Instead of this value, let's try and add 0 to this one. No error. So the problem is somewhere here. And if we try and do this, there is no error. So this actually shows that the problem is with adding unsigned and signed. So what can we do about it? We can actually, what can we do? Let me think. The CTCSS, that's unsigned. Yeah, so the value from the lookup table is definitely signed. Then we just find the correct value. Then we take the 12th most significant bits out of it, then fill the remaining bits, most significant bits, with either 0 or 1, depending on the sign. Yeah, so that should be signed, I believe, not unsigned. No error. All right. Okay, so the next step would be to try and synthesize it and see if the design can be actually mapped onto the FPGA. So we're going to try and do that. And in the meantime, oh, of course, you can go grab some coffee if you are not asleep yet. Yeah, so in the meantime, let's focus on what's going on again. So you've got the CTCSS encoder that generates a sine wave that's being output here. And just by the way, when we calculated the frequency tuning word for the NCO, for the phase accumulator, we actually took into account the trigger input frequency. So that's 400K. So just instead, if you are thinking, what's that for? And this value is actually the length of our phase accumulator. It's 21 bits. So all of that combined gives us the value that we have to add over and over again to the phase accumulator. And then when we take the 10 most significant bits out from that, we should be able to get a sine wave of exactly this frequency, plus or minus something, some error. Because of course that value is not an integer. We're using rounding here. So that's a rounded value. All right, so looks like it might work. Keeping my fingers crossed. So after this process is done, we take this value and add it to the value from the register 9, which in our case is a sine wave from a signal generator, 1 kilohertz sine wave. So after running this, we should be able to see 2 peaks in this spectrum, and not just random peaks, but one at 127 hertz, so somewhere around here. Yeah, so after the signals are combined together, that signal is used at the frequency modulator. All right, almost done. Yes, we are going to regenerate the netlist data, and we are going to inspect it because it's very wise to do so. Yeah, so we've got the register 1, then part of that register, allegedly 6 bits, gets fed to the CTCSS encoder, and the output from that gets combined with the register 9, the value that's held in register 9, the signed value, 16 bits. And we can, of course, tell that it's right because we've got 16 plus 16. So the synthesizer got the value right. Well, I would be surprised if it didn't. All right, and then the sum of that is routed to the frequency modulator. So now let's go ahead and actually program the FPGA with the new code. And when the process is done, I'm going to reset the FPGA and then reset the STM32. All right, so the process is done. Now resetting the FPGA. and resetting the STM32. Something looks, the spectrum looks okay. Let's take a, maybe this is more readable. So the spectrum is okay. Let's take a look at the frequency spectrum of the baseband. And yeah, we've got the peak at 100 and around, because we can't exactly tell what's the exact frequency. But yeah, we've got the peak for the CTCSS tone. Unfortunately, I don't have a radio that supports analog FM on 2.4 gigahertz. But there is something I can do probably. I can take my Baofeng and tune it to like something in the 70 centimeter band. And then we can tune the 8086 to something in that region. So we can actually see if the 1 kilohertz tone gets through and it's audible in the handheld. So actually, let's do that. And to do it, my setup right now is very simple. I've got the 8086 board with just a very small SMA antenna connected to it. And as you may know, the module that I'm using with the 8086 has two SMA connectors on it. And one of the connectors is used for the sub-gigahertz band, while the other is used for 2.4 gigahertz. So I've got the SMA connector, the SMA antenna connected to the 2.4 gigahertz port. Now I'm going to disable the 8086 so it doesn't transmit. Move the antenna to the other port. All right, that's done. Now let's modify the code that's running on the STM32, and let's change the frequency. Let's do two things at once, at the same time. Let's change the frequency to this. Looks good. Yeah. Okay. So let's program the STM32 with this. And then let's change the frequency in the spectrum analyzer to 433.475 megahertz. Yeah, so that's the signal. Hello again. Now let's take the Baofeng radio. I actually didn't expect that to work, so I didn't prepare the radio. Yeah, let's set it to 433.475. Yeah, that's the beep. Now let's try and let's actually confirm that the CTCSS is enabled in that radio. So that's somewhere R-CTCS, R-CTCS. That's the menu entry in the Baofeng UV82. That's the one I'm holding in my hand right now. So the beep is there, but the CTCSS decoder is off. So let's turn it on, and let's set it to 127.3 hertz. Yeah, the tone is still there. Now let's try and change the frequency to, let's say, 206.5. I can't hear anything. Yeah, okay. So let's try and do this. I'm going to leave the Baofeng radio set to 206.5 just by the microphone, but I'm going to turn the volume down. So the Baofeng actually detects the carrier, but since there is no CTCSS tone present, it's not going to enable the squelch. So let's move it here. Yeah, much better. All right, so the Baofeng is just right to the next to the microphone. Okay, so this is not going to show us anything meaningful. We need to change the frequency of the USRP to something else. And that's 475 E6. Yeah, that's it. Okay, play. In the meantime, I need to check my private messages. Yes, that's the signal. Yeah, so large 1 kilohertz peak plus 127 megahertz hertz hertz peak. Okay. Quick look at the chat. By changing into a value close to the one on the TX, like, can you explain this to me? What I'm going to do is I'm going to change the CTCSS tone in the OpenHT to 205.3, if I remember correctly. Let's take a look at the table. 203.5. So that's the new value that I want to use. So let's recalculate the tuning word. 203.5. Yeah. So that's 42B. Now, if I take this value, of course, this is only for debug purposes. Okay, we are not going to have this in a real end product. Where's that? 42B. Yeah, 42B. So the next step would be to make this a little bit easier and automated. So we need the map. So instead of punching in the values and regenerating the code and flushing the FPGA over and over again, we will have a very simple setup that we are just going to write a value to register 1 and expect the CTCSS tone just to be present in the signal. So when this process is done, I'm going to reflash the FPGA, and if it works, I'm going to grab something to drink, and then we can proceed. I hope that's okay with you, and the stream is not too long. Well, I can talk like that for hours, so, well, you know me. Okay, I've seen the comment. So the value that we have used here was for 127.3. That was the value that we have used previously. So now the radio, the OpenHT transmits 127.3 hertz tone. And in the radio, I have actually used that exact value, 127.3. Yeah, it matches. And there's the beep. And if I change it change it to something else, like, what's the closest value? 123. Yeah, 123 hertz, and it doesn't work. I have to set it to the right frequency to make it work. And let's try the other value, 131.8. Doesn't work either. So I have to set it to the correct value to make it work. So that was a false alarm, Morgan. I believe. Or maybe I'm wrong somewhere. I don't know. You'll tell me. All right, so I'm changing the value back to 200 and 203.5 hertz. 203.5. Because I believe that's the value that we are going to have in just a second. 42B, yeah. All right, this is done. We don't need to take a look. We don't need to look at the netlist analyzer because nothing changed there. We are going to reprogram the FPGA now. Of course. All right, so the process is done. Resetting the FPGA. And by the way, guys, thanks for watching this. Actually, we are a bunch of nerds that like this kind of stuff. Actually, I'm doing this every day, basically. Okay, so resetting the STM32. Yeah, so we've got the beep, so it works. So what is needed is, what's missing is we need a simple map from a 6-bit value to the value that we pass using the test signal, or a signal that's called test. So I'm going to finish that in just a second. I need to grab something to drink, and I will be back in about 1 minute. Okay, I'm back. Actually, it's getting really, really warm in Warsaw. I believe it's 18 degrees centigrade. I'm not freezing. Okay, so I've got my Baofeng. Yeah, nice beep. I need to change the frequency to something else. Or actually, I'm not going to touch my Baofeng right now because we are going to need it later on. All right, so what the problem is, we need a map between the input value that we have right here, that's a 6-bit value, and this value. So we need to store that in some way. Now, if I only remembered, how do I do that? Probably we can take a look at the lookup table. Yeah, let's do this. Let's copy this part. Yeah, might be a good idea. Yeah, so let's try with this approach. what kind of type do we need? And how many entries from 0 to 50? Do we need to tell that it's an integer? I don't think so. It's an array of standard logic vectors. No, actually, that was correct. So 51 entries of standard logic vector. Maybe so normally we would have to punch in every single value from 0 to 50, but maybe in our case we can limit that to 0, 1, and 2. So the 0 would be there is no CTCSS present. Then 1 is some arbitrary frequency, so we can just pick one value for the frequency. And then the other one is going to be some other frequency. So we are going to have three options: no CTCSS, or one of the tones that are selected by us beforehand. All right, so that should hold three values of standard logic vector, 16 bits. Oh, actually we need 21 bits because the frequency tuning word is 21 bits. And that also means obviously this is needed. All right, so the first value would be no CTCSS. Now we need the value to be 21 bits, but you can't store 21 bits in this format in VHDL because it's going to cry. So we've got 16 bits now, 20 bits. And we also need a 0, one additional 0. I'm not sure if VHDL accepts this kind of notation, but we will see in just a second. Yeah, maybe that's better. Okay, so fortunately, it does. Okay, one more second to check the private messages. Oh, hello, Jay. No, we don't use freedom height degrees. We use centigrade. Centigrade is the best. All right. Back to the CTCSS tuning words. So let's try and fill the table with three values. The first one is already there, is 0. Then the last one is going to be 42B. Let's say that's. Let's omit the hertz. We all know it's in hertz. And this is going to be 127.3. And that was 29B, if I remember correctly. But I'm not sure, so let's compute that again. 127.3.9B. Right there. Okay. All right. So now let's try with Right, this is not needed. Now, what can we do? We can actually reuse this signal, and at the rising edge of the clock, we can just map the output from the lookup table for the CTCSS to the test signal according to the input, which is the 6 bits of this, all 6 bits of this signal. Or maybe we can do something else. Maybe we can just put the CTCSS lookup table here and use the CTCSSI as the index for it. Let's try that. I'm not sure if it's going to work because it's VHDL and nothing is normal here and expected. So let's try, and we probably have to cast that value to unsigned, but I'm not sure. Let's try. Okay, maybe integer or to integer. No. CTCSSI. That's 6 bits, of course. Maybe that's the problem. No. Unresolved, unsigned. The lookup table holds standard logic vectors. So it has to be cast to unsigned. Okay, you know what? Fuck it. I'm going to bring back the test here. Okay, no errors. And now I'm going to assign a value from the lookup table to the test. And I believe it should work. And if it doesn't, we are going to see what's going on in more detail. Maybe this is actually an equivalent of what I was just trying to do just a few seconds before. So the test should get the value of this constant, and the index for that should be this. Let's try with only this. Of course, expected integer. Unresolved, unsigned. This is crazy. But it worked. Okay, so if this worked, actually, we can try and take this. I think I'm using too much of the word this. We can try this. Yeah, we can go back to here, back to this place, and replace it with this. Yeah, so the test signal is not needed anymore. And it worked. Okay. So let's try and do this. Let's synthesize this design. So we should be able to tell the FPGA which CTCSS code to use just by writing to register number 1. And we can do it very conveniently using HTerm, because I've got the STM32 is actually a part of the Nucleo board, and within the Nucleo board, the USART, the UART, the UART is connected to both of the, like, there are 2 STM32s on that board. One of them is used for the SWD programmer, and the other one is the target. So So the UART of the first one is connected to the UART of the second one. So you can actually, you don't need any additional cables to use the UART of the STM32 that is the target. So right now we've got something like this in the code. We've got an interrupt on one of the UARTs, and after receiving it, we set the flag that we have just received some command over UART. And then we check what the command was. We actually send the data to the FPGA over SPI. So we send 4 bytes, that's 32 bits, over UART to the STM. Then the STM32 just passes over that data to the FPGA. So we can write to a given register very conveniently. So we are going to do it. And to write to a register, the first byte of the address is, of course, 80. That's because the most significant bit tells if it's a write or a read operation. Then we've got the address, the lowest, the lower byte of the address, and that's 1 in our case. Then we need to calculate the value for the CTCSS. So initially, the default value should be 0 in that register, so no CTCSS. So the register should just hold the value of 0. But if you write a value of 1 in the correct part of the register, exactly this one, we should be able to change the CTCSS that is being transmitted by the OpenHT. So that's 1 shift left by 2. That's 4. Simple arithmetic. Yeah, that's 4. All right, this process is done. We are going to reflash the FPGA. Then in the meantime, I'm going to turn on the Baofeng, change the RCTCS. the menu entry is missing one character. I don't know why. Anyway. All right, so right now it's set to 203.5 hertz. So if we set the register to 0, we shouldn't hear the beep. If we set it to 1, we shouldn't hear the beep either. But if we set it to 2, we should be hearing the 1 kilohertz tone. So I'm going to leave it just like it is. I'm going to put it just by the microphone. All right, so the process is done. Now we are going to reset the FPGA and reset the STM32. You can see that the spectrum is actually showing that there is a modulation signal, but that's 1 kilohertz. At least I believe it is. Yes, that's just a lonely sine wave right there. Okay, so let's now proceed with the register write. So let's go to HTerm. And let's try with writing 0. So that should change nothing. Actually, that's interesting because after a reset, we should be getting 2 bytes from the STM32 telling us that everything is correct. So let me double check that before we proceed. So we tuned the 8086 to this frequency. Okay. All right, so we are reading from the wrong register. You are transmit. status register. Yeah, so that should tell us what's the status of the 8086. So if I remember correctly, those values are here. That's the command. That's the transceiver state. So the 3 least significant bits should tell us if the device is transmitting, receiving, sleeping, doing whatever else. But for some reason we are not getting those 2 bytes. But we should be getting those. What's going on? Okay, it's there. False alarm. All right, so the 34 tells us that the chip is actually 8086 RF215, and the 4 tells us that we've got transmission ongoing. All right, so back to the CTCSS. Let's clear this. We don't need it. Let's proceed with writing value of 0 to register 1, and that should change nothing in the spectrum. So we should still be seeing the same peak. Yeah, no CTCSS. All right, as expected. Now let's try and write a value of 4. That should give us a peak at 127.3, and the Baofeng should still remain silent. Yeah, there's the peak, and Baofeng is quiet. So let's try with the other value, and that was 2. That's 8. Yeah, so we should now hear a beep. Yeah. So let's get back to 0 because I don't want to listen to that. Okay, no tone, no beep. So it works. So guys, I think I'm done here. The only thing that's missing is the table with all other values for the CTCSS tones. So if you want to help me out and help out the M17 project, you can actually take this equation and replace the frequency with all the tones that are in the list. And the list is available right here. So for each entry, you need a value calculated using this. So let's take an example of 151.4 hertz. Yeah, so that's the value that should go to the table. And we need to repeat that process for every frequency. Oh, there's one more thing that we are missing, actually. I mean, the code works, but it's not very elegant to... or maybe it is. Because if we set the CTCSS, the tuning word, to 0, it means that the lookup table should output zeros. So I believe that's pretty safe. So we don't actually have to check if the input word, the CTCSS_I, is 0, and then just do nothing, and instead just set the tuning word to 0. So there are like 2 concurrent options that we can do here. And we have picked this one just by accident. So you can either set this value to 0 and expect the lookup table just to output zeros. So that's nothing. Or somewhere in the code, somewhere here, check if the input code for the CTCSS is 0, then don't perform any of this. So that's basically an equivalent. And instead of increasing the phase, advancing the phase accumulator, you can just set it to 0 and wait until there is a non-zero value for the CTCSS selection code. Yeah, so that's it. I'm going to push the code to the GitHub repository later today, and see you next time, guys. That's it from Wojciech Sierra Papa 5, Whiskey Whiskey Papa, for the M17 project. 7-3.